Welcome to thru.
They don't have middle names on them. What? Like
Hello and welcome back to Calculus2. This is the last section of Chapter 7, and it is Introduction to Differential Equations. So, Differential Equations course heavily depends on Calculus2. Everything you learn in Calc 2 is actually used in differential equations, starting from integration by parts, trig substitution, partial fraction decomposition. All of that stuff goes on for your Laplace transforms. Then later we'll cover power series. That will be Chapter 3. And then obviously a lot of integration and everything else. So Calculus 2 is the most important course as a prerequisite to differential equations. Now, differential equations is extremely large topic. It has many courses that are offered as differential equations. So the first course you would learn in differential equations, called Introductory Differential Equations, is just that. Introductory Differential Equations course, which we offer here as well. And that course is covering pretty much 1% of 1% of what is out there. The differential equations have a whole bunch of higher order differential equations, and then you have partial differential equations, dynamical systems, and it breaks into a lot of different stuff. Now, differential equations drives everything, actually. Differential equations are behind all of physics, and you know that engineering rests on the shoulders of physics. So differential equations is actually mathematics of physics and engineering and of us creating anything. Now let me show what is all this stuff is and how this works. This is just introductory, one lecture. We are not going to learn anything crazy here. The most rudimentary technique to solve separable differential equations and some simple stuff. Just to get the idea of what these things are, and then if you're interested, clearly you will take many courses in differential equations that are offered. So I will start with the definition that differential equation contains independent variable, function, and its derivatives. The implicit way to write this is that the differential equation is some kind of a function of, let's say, t, y, y prime, y double prime, y triple prime, dot, 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 equal to 0. So, differential equation must contain a derivative inside that equation. An example of differential equation would be xy prime minus sine y equals to 9. That's an example. Next, solution to differential equation is a function, not a number like you are used to by now. So you guys are used to equations that contain independent variables only. So you have an equation that says 2x minus 3 is equal to 9. Right? This is an equation that so you solve this equation and the solution is x equals 6. So this is what you had so far in life. Now your equation will say dy dx no coughing is equal to ky. Right? If you have a differential equation that looks like this, you have the first derivative on the left-hand side, you have a function on the right-hand side, your solution is a function. So solution is y equals ae to the kt, or kx, sorry, kx. So you have, so the first one is equation that you're used to. Guys, all of the equations you ever learned so far belong to these throughout your algebra and your pre-calculus, and later on calculus you have to solve a lot of these equations. Everything that you learned regarding equations so far in your mathematical career falls in the first line, because at the end of that equation, when you solve it, you get a number. Today you are, for the first time today, you are seeing the equation that has higher order solution, and that is a function. So now you have an equation that contains the derivative, and when you solve that equation, on the other end you get a function. Now you can do the same thing to check what you used to do before. If you say, well, I haven't seen any work, really 6, I don't believe it, well, check it. You take this 6, you plug it here, 2 times 6 is 12, minus 3 is 9. Perfect, it works. The same thing now happens with differential equations. You have the differential equation, you have the solution to the differential equation, you will differentiate that answer, plug it on the left side, you will plug y on the right side, and you will see that the two sides are the same. Just like you get on top that 9 is equal to 9, on the bottom you will have that ke to the ax, ke to the kx is equal to ke to the kx. So the first order of business for you to understand is that differential equations must contain first or second or third or whatever derivative in order for it to be differential equation, right? Have to have differentiation present. And so the first thing is that you have to have a derivative, and the second thing that the answer is a function. And then that function can be plugged in into the differential equation to for you to check that it is a valid solution. Now clearly solving differential equations should be much harder than solving the regular equations, because you have to worry about method. So you know the method. Again, there is a finite amount of methods that you have to learn throughout the course of learning differential equations, and then you will be able to solve those problems. So when you look at the equation 2x minus 3 equals to 9, you know the method for that because you studied that since algebra and you've been using it since algebra. So it's very familiar that you're supposed to add 3 to both sides. It's very familiar that you're supposed to do divide by 2 then, and you will have x equals to 6. So you follow a pattern. And if I change the numbers and change minus into plus, or if I shift the terms around, you still know what to do because it's always the same concept. The type of the equation, which is the linear equation over there, has only one way to be solved, and that is the sequence of removing everything to get x alone. For quadratic, you eventually have to square root. For cubic, you have to cube root, and so on. For exponential equation, you have to ln both sides. So you learn all of the tricks of the trade throughout the years of learning about equations, and you know what to do once you are faced with the equation. Now, differential equations are going to have the same thing, except you don't have years to learn it. You have 2 months or 3 months to learn it. So you look at linear equations of the first order, then of the second order with constant coefficients, with not constant coefficients. You look at exact equations, separable equations, equations that are solved by integrating factor, equations that have variational parameters with undetermined coefficients. All of these are different ways to solve differential equations in the first 2 chapters. And then you hit solving differential equations using power series, solving differential equations using Laplace transform, and then after that, numerical methods to solve linear differential equations, which is Euler's method, Runge-Kara methods, and so on. All of that stuff is in chapter 5 later. So it's a very broad thing. And then you get into systems of differential equations. So then you solve systems of differential equations because you can solve systems of these equations, right? I can write another equation like this and have x's and y's, right? And then have systems of 2 equations, system of 3 equations. Well, the same thing happens for your differential equations later. You have systems, and then once you go into dynamical systems, then you have even more things to worry about, critical points and sink and source and all of that kind of stuff. So there's a lot of things. And then finally, right, at the end of that, your elementary course on differential equations is over. Now, if you think about it, you are actually learning all of these methods and all of these techniques. And yes, it's crammed and it's, you know, really packed because, again, you spend a month in algebra learning how to solve these equations. Then you spend a chapter in pre-calculus learning how to solve quadratic equations and polynomial equations, and another chapter on logarithmic. Then you spend chapter on how to solve trigonometric equations in pre-calc 2, right? So it takes long time to learn those basics. Differential equations, everything is quick. Every lecture is a different method. And then if you are keeping up with primarily learning which method applies when, so you can use the appropriate method when you see a problem, and then obviously after that knowing the method that you have to use, differential equations are not an issue. But differential equations have a heavy, very heavy prerequisite for Calculus 2, and generally students that are very weak in Calculus 2 do not do well at all in DiffyQ because every problem pretty much requires some level of Calc 2 somewhere. So let's take a look at the most fundamental ideas of differential equations. So I said that that the entire physics as a branch of science is developed on the shoulders of differential equations. So differential equations are going to be this driving factor. So this is the way it works. We define that acceleration is given as negative g, right? So you start with acceleration is equal to negative g. Now, we know that acceleration is given as change of velocity in time. So change of velocity divided by change of time, and that is equal to negative g. What I have here in a red box is called differential equation. Now, differential equations have specifications that you look at the equation and you know what it is. Just like when you look at that thing over there, you say, that's a wall. You look at this thing, you say, it's a bottle. And you have an idea what the wall is used for, what the bottle is used for. So now, when you look at this particular differential equation, you say, well, first of all, this is a linear differential equation because it doesn't have derivative squared, it doesn't have derivative times the function, and all of these kind of things. So the first thing we will say, linear, ordinary differential equation, DE. We also know it's a first order. It's a first order because you have only the first derivative present. And we also know it's separable because you are able to separate v variables from t variables completely. V variables to be on one side and t variable to be on the other side. So these are the specs that this particular differential equation would have. It's a first order because it's a first derivative. It's linear because there is no dv dt squared, there is no y squared, there is no sine of y. So all of those kind of things will introduce what we call non-linearities, right? Squares, cubes, square roots, all of that kind of stuff. If it's applied, so it's a little bit trickier than that. linear differential equations are allowed to have coefficients that are nonlinear functions. That's fine. But you are not allowed to multiply y with the derivative. You are not allowed to square y. You are not allowed to square the derivative. You are not allowed to take a square root of the derivative. All of that stuff makes differential equation nonlinear. So if you are asked to classify, differential equation, one of the classifications is it linear or not? Next is what order it is, i.e. equal to the highest derivative present. And then separable. Now, separable differential equations. Separation of variables is the most rudimentary method of solving differential equations. So that is the first method you learn. It's covered on the first page of your differential equation textbook. And you are learning technically that one immediately. Immediately you're learning how to work out separable differential equations. Now, I have some physics over here. And as you can see, I did not talk physics. All I said is, let me define acceleration to be negative g, right? Acceleration of gravity. So let me define acceleration to be negative g. I want negative because it pulls down. And then I know from physics that the acceleration is change of velocity and change of time. And now I know that this differential equation is separable, so I am going to separate variables by leaving dv on the left-hand side and pushing dt to the other side. At this stage, I integrate both sides. Note that negative g is a constant, so I'm just integrating dt in this case. Integral of dv is v, and on the other side I have negative gt plus some constant c. I am going to call that constant c v naught, initial velocity. So if you ever wondered where are the physics formulas coming from, the ones that you are generally either memorizing or writing on a piece of paper, so you're taking the test, right? Because they allow you to. Here is what we have. We have that velocity is given as velocity initial minus gt. You have seen this formula in your physics courses. You have seen this formula. You might know this formula as velocity final is equal to velocity initial plus acceleration times time. This is the form that you memorize, that you'll know the formula from differential from physics. Now I'm just giving you the same formula, except instead of a, which I could have had if I wanted to, right? I have negative g, making sure that this is the equation for the free fall. And now if you take a look at this equation, you understand that the velocity of the object depends on initial velocity of the object, and then also the gravity part, which is pulling on that object towards the center of the Earth at all times. So now, as we are developing this further, we say, why stop there? Can we just define that the velocity is change of position in change of time? Let's put dy there. Change of, let's say, height in time. Because it's the change of position. The velocity is changing position. Acceleration is changing velocity. So acceleration is changing velocity, and then velocity is changing the position. So now, we have another linear separable first order differential equation that we can work on. And again, it's separable because why is there a dot over here? So V0, there we go. If you notice, the entire right-hand side is a function of t. So, by bringing dt to the other side, we are separating variable y from the variable t. Because on the left-hand side, you only have y, and on the right-hand side, you only have t's. So now, dy is equal to v0 minus gt and everything dt. That's the one that went from left to right. Now we unleash the integral. And what we get is y equals, and on the right-hand side, I'm integrating in respect to dt. So I have v0t. Each constant will pick up an exponent, right? For if you're in a polynomial domain, obviously. So v0t, and now I have to integrate this piece. Well, clearly it's going to be negative, right? And I have to so I'm integrating, right? So it's negative gt squared. And then we have plus c at the end. Guys, if you forget plus c in chapter 7 on any of your integrals, it's just minus 1 at the end of the problem. If you forget plus c in the solution to the differential equation, many things crumble after that. So you absolutely have to have this plus c. Now I'm going to define this plus c to be initial height, and now the equation over here that is given to me is, oh, it was t squared over 2 when you integrate, right? So we have negative 1/2 gt squared plus v0t plus, and I'll call this y0, and there is another equation. All right, ready for some experiments? Since it's physics?
Yeah.
There's the object, right? Now this object is going to fly over there. I have also this object so that I can repeat the experiment. So now what's going to happen is I'm going to throw this marker, and we're going to see if this formula makes sense. So, here we go. What kind of path did it take on? Observe the path. What was the path? It was a downward opening parabola. The path looked like this. Do we see negative x squared? Is that right? So in time, when I graph the height at which the marker is, in time, we see that the progression of this marker was, right? The progression of this marker was parabola, which it had the maximum point, let's say somewhere over here was a maximum point, and then eventually hit the floor. What are all of the specs that are important? Well, clearly we have the gt squared term because the gravity will be pulling on this at all times. Move on to the next term. Velocity. Initial velocity is how much of this I give to the marker. How much of a throw, of a punch, how much do I pack into throwing the marker? If I put the same amount as I did before, right? As you can see, parabolic. I can put less effort, right? It's not the same. So if I use less initial velocity, v0, then the height to which the marker is going to go is going to be lower, because that's what we are measuring with the last equation, the height. Finally, we have y0, which is the initial height from which you are throwing. It is not going to be the same if the 5-foot person and the 7-foot person, right? So person is tall 5 feet and the one that's tall 7 feet, it's not going to be the same for them to throw. The reason why basketball players are generally very tall, right? They're very tall because the hoop is all the way up. And the parabola for them, right, is less effort if they're taller. That makes sense because the hoop is on the whatever standard height for the hoop is. You don't get to change that because you have a lower, well, you don't know with the SGWs today, but if you have a team, then maybe you have to lower one hoop so it's fair for everyone, you know. Otherwise, terrorists win, I guess. I don't know. Whatever the arguments are. You see that every aspect of the formula is actually present in physical reality, which is what's called physics, right? Now, we used differential equations to develop the formulas which you have seen and had to memorize in your, at this point, rudimentary physics courses, because this is the intro to physics right there, right? So, this is what differential equations are used for. I say few words, and then you take those few words and you write the differential equation, which when you solve using the methods from differential equation course, you come up with a function which governs the notion that I was talking about. Let's go now and switch gear from physics to biology / environmental, right? Because we're going to talk about population. Population, number of people, number of bacteria, population of rabbits. So generally population, right, is going to be maybe even sociology, but, you know, it's biology deal. Let's write a sentence. So I'll call this population. The change of population in time is proportional to population. This sentence makes sense. The change of population will be proportional to population. Let's think about it. How fast is population going to change if you have just 2 people roaming around? Or 2 rabbits roaming around, or a bacteria roaming around, whatever it is. Not going to change that much, right, in time. Because only 2, right? In case of humans, it takes 9 months to cook the baby, right? So,
how is the walnut?
What is it? he said it like he was pregnant. Just be quiet. So,
You didn't get fatter when you had your first kid?
What happened?
You didn't get fat when you got your first kid?
No, his kid is still alive.
Did you get fat?
Why would I?
I didn't get fat.
It's called sympathy weight. You're a nice guy. Yeah. I never did that because then we can still go on the same escalator. Anyway, so the change of population is proportional to population. When you have a huge population, population grows faster. When you have small population, population grows smaller. So the change in population is going to change proportionally. Also, if you have a battle between 2 people and one shoots another, right, that's death. Well, 1 person dead. if you have a battle where 100 people is shooting at another 100 people, that's big population fighting, right? Much bigger than the population one-on-one. Well, a lot of people dead, right, in that case, because, again, change in population is proportional to population. Now, whether it's birth or death, right, this sentence makes sense. So when you make a statement like this, the change of population is proportional to population, now you are ready to write your differential equation. The change of population in time, you should know this from Calculus 1 course, something like this means change of population in time. You write that as a derivative. The word is, let's put that blue, is equal sign. So change of population in time is simply going to be denoted as the derivative. And you write dp, dt, and our word is equal. Proportional to population, let's go with, I guess green, I don't know, is going to be kp. In mathematics, when we say that two variables are proportional, we will write y equals kx. If the two variables are inversely proportional, we would write y equals k over x. So in mathematics, I don't care whether it's algebra or differential equations or calculus 17, whatever it is, if you say that two variables are proportional, you will be writing y equals kx. So you see the structure kp because whatever was on the left is proportional to the population, so equal kp. It could be proportional to the square of population. It could be proportional to square root of population. It could be proportional to 3 less than square root of population, right? And square root of t plus 3. And every single one of those would be times k, right? Because that's constant of proportionality, which is always there, right? You can also think of it as a scaling factor. So now you have seen the transformation from everyday talk and something that is readily accessible to all of us if we understand the language, to translating that into mathematical equation, which is in this case differential equation. And now we are supposed to solve this. Again, all of the specs that we talked about before, because obviously that's all we have in this introductory lesson. A separable equation, which is the linear equation of the first order. You only have the first derivative, you have the ability to separate variables. You separate variables by placing all of the variables of one kind on one side and all of the variables of the other kind to the other side. You can keep this k on any side you want. You can have k on the right or 1 over k on the left, whatever, right? Because that's a constant, it doesn't matter. So, to solve this differential equation, you will first, to solve this differential equation, you will first do separation of variables. So you will put all p's on the left and all t's on the right. And it's easy to achieve here. So dp divided by p is equal to k dt. So dt goes on the right because that's the independent variable, and p, which was actually the function we are looking for, goes on the left to join the dp on the left-hand side. So now, when we separated variables, so now let me just put the arrow and say variables, are separated. Meaning all p's on the left, all t's on the right. And those are the only variables we have. So now that I have this done, I integrate both sides, And then whatever happens, happens, right? When I integrate, observe that I integrated only dt, because k is a constant, so it doesn't matter whether it's in or out of the integral. We will be rewriting it anyway. What do I get on the left-hand side when I integrate dp over p? What do I get? Yes, very good. We will get ln absolute value p. On the right-hand side, what do I get? kt. Keep talking. Plus c. You drop that plus c there, the whole thing goes to garbage. All right, so now we solved our differential equation. Well, we really don't like it, right? Because the function which we are looking for, which is the function that tells us how population changes, is buried inside ln. How do I free it up? E both sides. Nice. So now we e both sides to free up function p. As soon as e and ln cancel, you don't need any more. I'll just put p. You don't need absolute values anymore, right? You need absolute values when p is buried inside ln, because you will not be able to use negative numbers. But now, once e kills ln, you can just put p, no need for that anymore. Now, on the other side, you have e to the kt plus c. Now, in mathematics, when you are adding exponents, you know that x to the m times x to the n is x to the m plus n. This is your elementary algebra. So now, using that rule, I can split this into e to the kt times e to the c. Now, e to the c is constant. And I will call that e to the c p0, initial population. Remember how I did the same thing for initial velocity earlier, and I did the same thing for initial height for the v0 and y0 when we did the physics kinematics? So now I'm doing the same thing for population. I'm going to take this constant term, e to the c, and I'm going to make that into initial population p0. So now my formula becomes p of t is equal to p0 e to the kt. We have solved differential equation. What you see here is the equation which you know from pre-calculus course, right? You were told, use this to calculate the population. And then you go and you memorize this thing because you had no clue where it comes from. Now you do. A simple differential equation, and I say simple differential equation because every separable differential equation is simple. So you solve the differential equation using separation of variables. You have your, are you happy now?
No, I'm so.
So, and you have your answer. Now, what's left? Well, first off, as I said, what's left is to check that the solution you have, maybe I should, let me point the arrow into this and say solution. You see it's a function that depends on time. Population changes in time. Whether the people are getting born or dying, it takes time. Right? Either way. So population can change up, population can change down over time. Depending in which regions of the world you live in, some countries are growing their population and some countries decrease their population. Japan is one of them. The population is decreasing in Japan. So now, first order of business for me is to check and see if this is the solution for dpq. So now let's go and check. So I need to check dp dt equals kp with a solution that p is equal to p0 e to the kt. Well, dp dt, which is the derivative, is going to be p0 k e to the kt, because the derivative, you copy p0, derivative of e to the kt is e to the kt, and then the chain rule kicks in for the exponent. Derivative of kt is k. So the overall derivative is p0 k e to the kt. Now, you plug in. On the left-hand side, you have p0 k e to the kt is equal to k times p0 e to the kt, because that's what p is. And you see it's equal. So good to go. P0 times k, or k times p0, it's commutative, so we're all good. So now we check the differential equation. This is one of my favorite features of differential equations. I told you earlier that I was very fond of Calculus 2, up to the sequence and series part, because it was integration. And I like the fact when I'm right. That's the reason why I research the facts all the time. I don't care when someone starts yapping about their opinion, which is irrelevant. So, exactly. So, if you have all the facts, then you have to be right. So I like the integrals, because when I'm done integrating, I differentiate the answer. If I get the function I started with, perfect. Right? It's great. I also, for that fact, like differential equations, because every time you solve differential equation, if you're not lazy, or if you care, right, you can always differentiate, plug everything back in, and make sure that it works out. Just like you were supposed to plug in 6, and that very first example that we talked about, right? If you care, you're sitting in elementary algebra class, and you care. So on the exam, you solve x equals to 6. The problem doesn't say check or whatever. They just say solve, right? Who cares? Well, if you care, you just take that 6, you plug 2 times 6 is 12, minus 3 is 9, and 9 is equal to 9. That 6 is perfect, right? So you can have the same attitude towards differential equations. In a differential equation, you look at this and you say, let me check. So you take your function that is your answer, and you plug that function and its derivatives in the differential equation that you had at the beginning. And if it checks out to get the same statement that left is equal to the right, you're done. That's what it is. So there's that. Now, there are many applications. Everything we touch and see is application of differential equations, because it governs the entire physical realm around us. Everything that we build, everything that we design is resting on the shoulders of physics that is derived through differential equations. So, you know, I hope you might have some appreciation for it. Another example of this would be environmental issues and things. We don't have our environmentalists with us today, but we can include it in a stream. So the environmental issues are concerned not just with the pollution, they're also concerned with amount of garbage, amount of radioactive garbage. Now new concerns are being raised with the level of drugs like the pills that you get for people being sick and stuff like that. So that kind of chemical drugs are starting to be found, traces of that in the running water, in the underground waters, and all of that. So all of these are big concerns, right? So now when you're talking about drug has to metabolize in the body, has half-life, so you can do we've seen those problems in the previous chapter. We can do the math for that. Also radioactive decay, so you have electricity that is produced today. It's mainly produced by thermonuclear plants, which is nuclear fission, and the nuclear fission leaves behind the radioactive waste, which we don't have solution on dealing with the radioactive waste. So what we do is we either throw it in the ocean or we throw it in some mountain somewhere and just leave it there, because it's thousands upon thousands of years for something like that to dissolve to levels that would be safe or manageable by humans or animals, right? So whatever grows in that area has, 3 heads and whatever. So now we can use differential equations to develop mathematical models which would show what is happening. Now, we have to be very careful when we are formulating differential equations, because if you oversee the factors that need to go into the differential equation, you create the function that you get at the end might not represent your problem fully. It might only partially represent of what you want to measure. And this population problem is a perfect example of that, because if you look at the answer that we have, so answer analysis. If you look at the function given by pt equals p0 e to the kt, you see that this cannot be the master population equation, for a simple fact that this model allows population to grow without bounds. And we know that our planet cannot support infinite amount of either people or rabbits or bacteria. I don't care what infinite is infinite. So even if you're talking about bacteria rather than people, and you can't even see bacteria, how small it is, it's still it's exponential growth. So I don't care whether it's bacteria or people or rabbits. It's equally bad on the X. So when you have infinity of bacteria, clearly they cannot occupy bounded space. And our planet, might be a shock to some, is round and finite. So that's what we have. So now, to prove this point, we take a look at the limit t goes to infinity of p0 e to the kt. And as you can see, right, p0 is a constant, k is a constant, but e to infinity is infinity, so the whole thing goes to infinity. So we see that this model, even though might be good locally to compute population, 5 years ahead and these kind of things, sure, 5 years ahead we do not expect to have infinite amount of people, and this formula will not predict that you will have 5 million, infinite amount of people next year or in next 5 years or whatever. But if you let time grow without bounds, it does suggest that the population becomes infinite. And you know that that is not the case. Because I don't care how much time passes. Well, there is expiration date on the planet, but whatever time passes, you will always have the same size object. So you can't magically have, 7.5 billion, well, 7.4 billion we have today, then you wait infinity and you have infinite amount of people, and they're still all over here on the planet. That doesn't work. So what we have is different types of differential equations and different types of population models that do much better job on the long run. This formula is very simple to compute, which we did. Very simple to compute, and because it's very simple to compute, what you have is a model that actually doesn't work on the long run. So it's okay to use locally. What's going to be population of Earth next year? What's going to be population of these rabbits in 7 hours? Right? That's technically not rabbits in 7 hours, bacteria in 7 hours. Rabbits take longer than 7 hours to multiply, right? So there is also this analysis part, because again, differential equations are highly applicable, right? All of physics rises from differential equations. From that, physics engineering rises. So technically, right, if you cut out the middleman, which is physics, right, you go from differential equations into the device that was created by using differential equations. So differential equations are everywhere, and they give rise to everything we have. There is an R missing over here. Answers.
I was going to say that.
But who cares, right?
You ever had the itis?
I don't know what saying.
You know what the itis is? Like when you eat so much you fall asleep?
No. I have a lot of exercise in that region, so I don't pass out after I eat.
The itis.
Right now? There's a pillow behind that cabinet.
I don't know. I won't think on when I wake up.
And you might have some of the fire blankets in the security over there. So.
But security, I don't like talking to them. They rent them all cops.
Anyway.
Yeah. My boy, you got glasses, you still squinting. What's going on?
It's really small.
I heard you. So if you had an iPhone, you just pinch it open and it would become bigger.
I just did.
My boy. No, it's just crazy.
If I had iPhone, I'd probably...
You'll live, but sell it.
No.
What phone do you have?
You got an Android Kabooti. You got it from Walmart. Yeah,
I heard of those, didn't
called
I?
the Android Kabooti.
I'm just considering if I should do this problem or not. Maybe I should. Let's go back to physics and so, you know, for fun, what you can do is you can do the project. I assign this sometimes as a project, which
why
means
don't you assign the project to it?
actually maybe I should assign. Let me assign this problem to the project. I haven't done that in.
Can you assign the project today?
This is how much it takes to solve it. So.
Let me see
All I
that.
can see is two pieces of paper.
Exactly. That's
So
enough.
that's easy. I can do that.
So, what we are going to do now is we're going to talk briefly about one of the project problems for you guys, since we have separable differential equations in 7.9. Your project will probably be assigned this weekend, and it is due the day of the final exam. You have 3 weeks to solve 4 problems, write up the report, and then hand that stuff in the day of the final. Not the day before the final, the day of the final. And the project will contain what I have here, Newton's law of cooling. So Newton's law of cooling is used to calculate the time that you need to cool the object from certain temperature to certain temperature, or to heat the object from certain temperature to certain temperature. Generally, I like to assign this project and problem when is the fall semester, if I teach Calc 2 or differential equations, because it's Thanksgiving and you will be making turkey, right? Thanksgiving turkey, so you can actually figure out exactly down to a second how long you have to bake the turkey to reach perfect 160 degrees. Now, students, when I assign outside of this, they just go to ShopRite, they buy a $10 chicken, and then they bake chicken in the oven If you are vegetarian, you can still do the project. There's not a problem. I'll eat the chicken. Don't worry about it. You still get to bake, right? Now, you can't really do this on leaves and stuff, so it has to be something concrete. Vegetarian? Vegetarian? You? No. So what we are going to do is you will look at Newton's law of cooling. And Newton's law of cooling will have a sentence which will say something that temperature is proportional to the difference of the temperature of the environment and the initial temperature of the object, which actually makes sense. If you have hot coffee and you leave hot coffee in the environment of the room, the coffee will slightly heat up the atmosphere of the room, but the room will most definitely cool the coffee down to its temperature. So it is very negligent of how much the temperature of the whole room changes because hot coffee was introduced to the ecosystem, but it is very visible, right, when the huge room that is, let's say, at 67 degrees, right, it is, if you leave the coffee for an hour, 2, 3 hours, whatever, the coffee will be 67 degrees, right? So the entire temperature of the room will negligibly grow up, right, where the temperature of the coffee would significantly cool down. So the same thing goes for a turkey. You have a turkey or a chicken that it's at the fridge temperature of whatever it is. You can use the temperature probe to measure that, or you can just leave it on the counter to get the room temperature. So let's say that the turkey or chicken before going to the oven, right, is going to be at, I don't know, 71 degrees. Let's say it's 71 degrees in the house. So 71 degrees, that will be initial temperature of that. And then you put that in the oven. You have the temperature of the oven. You have the timer and all these kind of things. And you figure out how to go through the whole process of baking. You will be taking pictures. You will be also writing up the method that you, if you want to explain the seasoning and all that, you are welcome. That's okay. You can have a certain part of the problem to be, cooking recipe and all of that kind of stuff. And then most of the project and the problem obviously will be your calculations and explanation on the method of Newton's law of cooling, derivation of the equation you have to use, and then eventually calculation how long it takes. The cool thing about this is, obviously, I mean, this is what my projects look like. It's something that you actually do with your hands, and then also you take pictures, and you write a report on what you have done, and then also. So one problem probably will be cooking the chicken or turkey or whatever you buy. Maybe you want ham, maybe you want whatever it is. You will need the temperature probe, obviously, and a working oven. I've seen students bunch up together and then they cook one turkey or they cook one chicken and they eat it afterwards, and they all share data and then they all write their individual, right? You take your own photos, you take with a cell phone, and then you write your own report, and in that case 3 or 4 students, right, might be sharing the same numbers that they measured. That's okay as well. You don't really want to have 10 people in one because one chicken. I mean, I eat the chicken. I can eat the whole chicken. It's myself, right? You have 10 people around, then yeah, it doesn't work very well.
What if 8 of them are vegan? I'm not eating.
Yes. If any one of those people would like to be my friends, I would definitely be their friend because there's more real food for me. Anyway. The next part is, so that's the story of differential equations. So look, Newton's law of cooling. I just say look it up for the project.
Maybe. You definitely going to sign?
And the only, why not? And then the only, because I mean,
I'm still on
It's something that you eat at the end. It's not something that you waste. Here's another one that you actually have a little bit of waste, right? You take a piece of wire that you can cut. So definitely not this one, because this one is useful. But
it's called private property.
yes. Well, well. So you take a piece of wire that you can bend. You print a function, which I am going to assign in the project. You print a function, and then you bend this. You bend the wire along that function, and you tape it, and you take pictures of it. You make sure that the wire is cut to the same length as the printed line. Well, did we cover equation of the length of the line? Beautiful. You have mathematical formula. That's how you printed the function. You have mathematical formula, so you can use integral that you learned in chapter 6 to calculate the length of the line. Then, the one that you cut, you can straighten that up and use the straight edge to measure the wire. And those numbers better match. If they don't match, well, either you can't compute or you don't know how to convert units. That's it, right? So that's another one. You take pictures, you write up a report. Yes?
Are we doing like multiple projects or just one?
There's one project with 4 problems on it.
What?
So one problem is Turkey, one problem is wire, one